right. Well, it is time to go ahead and get started. And like I said, this is an optional lecture, so I guess I should just go ahead and go instead of waiting for people. Uh, Anybody have any questions before I get started? And also go ahead and chat me your first and last name. I'll just have that as a roll or attendance, even though, again, you're not getting punished or any kind of reprimand or anything like that as regards to missing days. It's just a matter of I can have a record of when last time you came. So by all means, do that. Looks like no one has any questions. We are going into chapter 19. Last time I actually completed chapter 18. And yesterday, I actually posted another video on my YouTube channel. It was a clean version of that derivation of the average velocity as calculated by the Maxwell distribution. I did it for you guys in class, but it was rushed, and at the very end, I dropped a couple symbols. I might have dropped a couple exponents and signs and all sorts of stuff. So rather than have you just rely on that possibly incorrect because it could have had some little arithmetic errors and stuff like that in it. So rather than just leaving you with that, I went ahead and did a clean one yesterday. It's been posted on there, and I think it's just called Maxwell the average or something like that. So, and it should be near the top on my YouTube channel. So go ahead and check that out if you want, so you can learn how to do it. This is a skill I expect you to be able to do. As you can tell, it's one of the skills that the actual textbook has as a problem to solve. In fact, they have the harder one, which is the average of the square of the velocity, which is the same thing that I did, except instead of taking 1 over n times the integral from 0 to infinity of v times f of v, it's taking 1 over n times the integral from 0 to infinity of v squared f of v dv. So what you do in that case is you still use the integration by parts like I did, but you have to apply it twice. You've got to do it once to get rid of the v cubed and make it a v squared, and then again to make it a v. So basically that's how you do it. It's just the same process repeated. So give that a try if you want. That is the kind of thing that I could put on your first face-to-face test. Of course, your first online test has been open, so you guys can go ahead and start that at any time. It's not due, I think, until some classes it's February 2nd, some classes it's February 1. I think yours is February 2, but I don't want you to trust me on that. I want you to check in Canvas and see what the due date on practice test 1 and online test 1 is. Remember, we don't trust the dates on Canvas with regards to MyLab and mastering homeworks because it doesn't necessarily obey the rules like it's supposed to. We trust the MyLab and mastering due dates on that, so keep that in mind as well. So let's get started on chapter 19. Chapter 19 is heat and the first law of thermodynamics, and it covers heat as energy transfer, internal energy, specific heat, calorimetry, solving problems, latent heat, the first law of thermodynamics, thermodynamic processes, and the first law, molar specific heats for gases, and the equipartition of energy, adiabatic expansion of a gas, and heat transfer, conduction, convection, radiation. So those are the subsections within the chapter, and of course, the chapters always open up with chapter opening questions. As I've advised you guys, it's good for your learning to actually answer these questions, take them seriously, answer them, write the answer somewhere, or at least remember the answer and your reasoning for it. And then later, as we're going through the book, you'll find the right answer, and you then can sort of use a scientific process or a scientific uh, the scientific procedure in learning how to do physics problems. So that's what the advantage is of asking these chapter opening questions and then having you answering them and then having you find out the right answer. So do that. I want to first off start by differentiating between heat energy and energy. So heat is energy in motion. It's actually a form of energy. Uh, that is being transferred from one object to another as a result of their difference in temperature. So that's what heat is. Heat is energy in motion. In fact, they used to think it was an actual fluid that the substances contain. We no longer think in terms of objects containing heat. Objects have an internal energy, but heat is a sort of a form of bastardized energy in that it's not as free and useful as energy in general. Specifically, heat is something that when you convert energy, like let's say kinetic energy, to heat, you're never going to get all that energy back. So if you put in, 100 joules of kinetic energy and you convert that to heat, then when you go to get that heat or that energy back out, that was heat is going to come out instead of 100 joules. It's going to be more like at least 90 joules or maybe even smaller, like 5 joules. It's a huge, huge loss. So in that sense, it's like a impure form of energy. Uh, but if you think about it, what it is heat is often the result of, as we learned, an object that is hotter has a higher average kinetic energy for its molecules than an object that's colder. So if you take two objects, one hot and one cold, and put them next to each other, the individual atoms and molecules of the hot one has higher kinetic energy than the average kinetic energy of the molecules and atoms in the cold one. So every time one of these atoms in the hot one hits one of the atoms in the cold one, and again, atoms and molecules are interchangeable words in this chapter as well. But when one of the atoms or molecules from the hot object hits the atoms or molecules from the cold object, that particular atom or molecule that was hit will then have a larger kinetic energy for a split second, but then that will reverberate because that particle will go on and run into other particles. It'll bounce off walls with higher energy, then hit other particles, and eventually what happens is that particular particle has now distributed its energy amongst numerous other molecules or atoms. And again, another atom or molecule from the hot object will do the same thing and the same thing and the same thing. So what you're seeing here is the heat transfer is literally like kinetic energy from an atom or molecule in a hot object being transferred to all of the hot, atoms and molecules in the cool object. And you can think about it that way, and you say, "Oh, well, how in the heck could I, take all these uh, crazy cats is what the atoms and molecules are acting like and try to get a certain amount of energy from each one?" That's a very low probability event. So that's why, or that's one of the reasons you can think about as heat being somewhat not necessarily destroyed, it's just no longer usable. So that's what the heat is, and the energy that the two objects had, the hot object and the cold object, that internal energy, the sum of all the kinetic energies, potential energies, and all the types of energies that the molecules or atoms had in an object, that is the internal energy of the substance or of the object. So that's another thing that we want to keep in mind, the difference between energy, heat, and then internal energy. Internal energy, of course, is a type of energy, and we can pull stuff out of it, but some fraction of it can be as a result of heat. So you're not necessarily going to get all of it. And in fact, we know from quantum mechanics, you can't, bring any atoms or molecules down to zero energy. So that's something else that we'll keep in mind. Oddly enough, all this stuff that we're using is mostly stuff within thermodynamics, but it's also, kinetic theory and what we call statistical mechanics. And those are largely statistical tools. But the one thing you know is even though we were using kinetic theory, statistical mechanics, and Newtonian laws of physics, you were actually able to get very correct results, even though we had no knowledge and used no knowledge of quantum mechanics. So it's really amazing how much, on average, even microscopic things behave in a macroscopic way that obeys Newton's laws of motion. So, anybody have any questions on that part? All right. So as I was telling you, they used to think that heat was a fluid, and that fluid was called caloric, and that's where we get the origin of the phrase calorie, which is now a unit of energy as well. And in fact, it was initially a unit of heat because they thought of heat as one thing, and then they thought of mechanical energy as another thing. And in fact, it was very distinct because energy, like kinetic energy, potential energy, all that was measured like in joules, whereas heat, the energy required to raise the temperature of water, for instance, was thought of as heat and was measured in calories. So the very fact that they used one system of units for one quantity and another system of units for the other quantity was saying a lot. It was trying to express to them specifically that these are different quantities. And what we're going to learn is, in fact, there's a mechanical equivalent to heat that James Prescott Joule actually discovered, and that's the first thing we're going to learn in this section, other than the stuff I'm talking about right now. Now, I will tell you that the calorie, a unit of energy, which again was originally a unit of heat, the calorie was defined to be the amount of energy required to raise 1 gram of water by 1 Celsius from 14.5 degrees Celsius to 15.5 degrees Celsius. Then the kilocalorie was defined to be the amount of heat required to raise 1 kilogram of water 1 Celsius degree from 14.5 to 15.5 degrees Celsius. So that's the formal definitions of the calorie originally. And that also, by definition, gives us the actual specific heat of water because it turns out the specific heat of water is the amount of heat required to raise the water. A certain amount of water, a certain number of Celsius degrees, and specifically, you can write it as 1.00 calories per gram Celsius degree as C, the specific heat of water. You could also write it as C, the specific heat of water, equals 1 kilocalorie per kilogram Celsius degree. So that's another thing to keep in mind. The British thermal unit is another unit of energy, and I think somewhere in your book it might tell you. I'm trying to remember if it was that book or a different book that I remembered, but it's on the order. It's something like uh, the amount of energy. A British thermal unit is the amount of energy required to raise 1 pound of water 1 Fahrenheit degree between such and such a temperature and such a temperature. So it's very similarly defined, but it's not something that we're going to use, except occasionally the author will give you a measurement in or a heat energy in BTUs, and you'll need to convert it using a conversion factor, which your book gives you. Okay. Another one, of course, is the joule, and the mechanical equivalent of heat actually makes a conversion factor before them. But I want you to understand that this conversion factor is way more than a conversion factor. It's a whole paradigm change where people realize, oh, wow, this stuff that was heat is evidently the same thing as the stuff that we call energy, and therefore there's a equivalency between what we call it mechanical energy and heat. So keep that in mind. So, with that in mind, I'm going to go ahead and share my iPad screen with you guys. And this is one of those times where I'm going to be using the examples from the textbook. So, if you have the textbook, electronic version or whatever, and open, it would be best. That way, you could read the examples that I'm going to read you anyways. But the main thing is, it's probably a little easier for you to follow if you have the ability to read and double check uh, what the exact examples say. So that's where we're going to move on. So the first thing I wanted to talk about, like I said, was the mechanical equivalent of heat. And you can imagine the experiment done in that case was more or less as follows. So what James Prescott Joule did was you can imagine a calorimeter or a beaker full of water, if you will. And he knew, for instance, that a certain amount of energy was required to raise water, 1 gram of water by 1 Celsius degree, and that amount of energy was specifically 1 calorie, and that would raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius, and it might take a little bit less or a little bit more to go between, say 13.5 and 14.5, and the same thing with going between 12.5 and 13.5, or between 15.5 and 16.5. That being said, we find out that it's mostly linear over a very large temperature ranges, so you can sort of use that a little bit. But if you're actually doing serious engineering work where you really need to know exactly what happens to something as a result of a heat being added to it, then yeah, you need to do yourself a favor and look up every individual specific heat in the range between the lowest temperature it'll be at and the highest temperature it'll be at, and then use that accordingly. So, anyways, what we had was a container of water like this, and in that container of water was set up a little propeller, which you can sort of picture like this, on an axle that actually came out of the water like this and had more or less a spool of wire or string on it, and that spool of string went to a pulley, and then from that string was hanging a mass let's say little m, and that mass little m had a height h above some point that they considered the arbitrary zero of potential energy. Now, in addition to having this mechanism that allowed this propeller to spin around, they also had a thermometer in here so that they could see if the temperature actually changed as a result of the spinning of the water. So that was another part of this experiment that we got to show you. So in addition to that, we have a little thermometer in here, and that thermometer could very precisely read the change in temperature of the water as the propeller spun. The argument being, as you guys have now learned from the previous chapter, that basically if a propeller is hitting individual atoms and molecules, then you expect that propeller is going to cause individual atoms and molecules to speed up. But if you wait long enough, those individual atoms and molecules speeding up will eventually sort of disperse throughout the entire liquid sample and cause all of the atoms and molecules on average to increase their kinetic energy, and obviously the average translational kinetic energy of the atoms or molecules in an object or in a substance is directly proportional to the temperature. So they did expect the temperature to rise as a result of these propellers, and then it's just a matter of letting the energy, which was E equals mgh, be equal to the heat, which was Q. Q is the symbol we use for heat. And what we expect is if you want to calculate the amount of heat Q that you need to add to a sample of substance to change its temperature by an amount delta T, then you expect that Q to be directly proportional to the change in temperature delta T. What that means is if you're changing the temperature from 15.5 to 16.5, that should be a lot smaller heat required than changing it from 15.5 to 155, right? Because it's 10 times larger. So, yeah, clearly Q seems reasonably proportional to delta T. It also is that Q seems reasonable to be proportional to the mass of the water. In this case, since I used a little m for the water or for the block hanging, I'm going to use a big M for the mass of the water in the cup. Okay, so we also expect the specific heat is proportional to the mass because obviously a itty bitty drop of water takes a little bit of heat to change its temperature, whereas a swimming pool full of water takes a lot of heat. So we expect that to be proportional as well. Uh, it also depends specifically on the substance being used, and you can just sort of stick some arbitrary constant in there, and then you might need yet another constant to relate the Q to the M to the specific heat and to the delta T. But what was chosen was no additional constant. We're just going to allow the total equation to be taken from Q proportional to MC delta T to Q is equal to m times c times delta t, where c is the specific heat of a substance. Okay, so it's another property of a substance. Like you can look up in a CRC manual and find the specific heat of copper along with the density of copper along with the boiling point of copper and the melting point of copper and all that stuff. Those are physical properties of a material. And of course, if it wasn't an element, then you'd have something like water. Well, you could look up the specific heat and all that stuff for it too. Same thing with other more complex compounds like sucrose and methane and CO2 and all that good stuff. So the idea was with James Prescott Joule, and in Great Britain, by the way, there is a beer called Jowls, and it's spelled Jaules. That's the same family. They got their fame by working obviously in thermodynamic realms, but that was because they were brewers of beer. They were also people that would actually bore out cannons to make cannons for the government and stuff like that. So they had a lot of stuff they were doing that was related to the generation of heat and the various other thermodynamic principles. So they became a very big name, and therefore we named the energy after them. So what James Prescott Joule found was, in fact, that when you set M times G times H equal to M times C times delta T, they were able to discover that in fact 4.1, oops, there I go again. I always leave off that one. 4.186 joules is equal to 1 calorie. Okay, I don't know why I wrote that joule as a subscript. I guess I just took my eye off the ball for a second. But one calorie, 4.186 joules is equal to 1 calorie. Now, there's also the dietetic calorie that we're used to, and the dietetic calorie that you're used to is called the calorie with a capital C. So, dietetic calorie is 1 cal, which is technically defined to be 1,000 lowercase calories, and therefore it's also 1 kcal. Now, in addition to this 4.186 joules equals 1 calorie, you could also say 4.186 kilojoules is equal to 1 kilocalorie. Now, again, when I took this in chemistry, for instance, this was just a conversion factor, though I suspect my teacher tried to teach me that this was a paradigm shift, but I don't recall remembering that, and I don't recall reading that. But that time I was still having a really hard time learning how to read science textbooks to get the information that I needed. I was doing as good as I could, but I was probably no better, probably way worse than you guys because I was such a poor student. I had read so little by the time I graduated high school. But the main thing is, it is a big paradigm shift, but it's also a conversion factor. So now you know a conversion factor between the joule and the calorie, as well as between the kilojoule and the kilocalorie, as well as between the dietetic calorie and the kilocalorie and the joule. So, your book does have lower down on the pages. It does have the BTU and other units of energy that have been used historically. One BTU, for instance, is 0.252 kilocalories, and that's 1,056 joules. Another unit that's used by gas companies is called the therm, THERM, and that's basically one therm is equal to 10 to the fifth BTU. So you can see how those are related. The main thing I want to do now is use this to make some sense of some of the types of problems. So for instance, example 19.1 is the first thing I'm going to do. So again, I'm going to read that to you guys, and I might even end up reading it twice, but the main thing is if you have it in front of you, it makes it a lot easier. So it says example 19-1, estimate working off the extra calories. That's sort of the title of the example. It says, suppose you throw caution to the wind and eat 500 calories of ice cream and cake. To compensate, you want to do an equivalent amount of work climbing stairs or a mountain. How much total height must you climb? So what we're looking at here is energy is equal to 500, and they used a capital calorie. Okay, so that means it's 500 kilocalories, like that. And what they want to know is how high would you have to climb to burn that up. So what we can do is we can first just pretend exactly how much energy or exactly what elevation you have to get for a potential energy to be equal to 500 kilocalories as we have here. So we can do that because we know that the potential energy is given by the symbol U. It's also used by PE. That's another way of saying it, but it's given by mgy, where the y equals 0 is set arbitrarily to some quantity. As long as you stick with it, as long as while you're using that figure, you'll be fine. So it's completely arbitrary what you call the zero of potential energy, but as long as you set it and then stick to it, you're going to be good. So what we want to do is set that equal to 500 calories, uh, dietetic calories. So we'll take the 500 calories, which are kcals, and what we're going to do is realize that 1 kcal, or excuse me, what we're going to do is realize that 4.186 kcal is equal to 1 kilojoule. So you can now see that the kcal cancels out with the kcal, and I'll take 500 and divide it by 4.186, and that gives me, oops, switched to red there by mistake. That gives me 119.4 kilojoules. That's technically, we can assume, if I assume the 500 calories is actually 3 sig figs, which is not necessarily a good assumption, but we're going to go on it anyways. If I do that, now I can set that equal to mgh. So I'm going to say 119.4 times 10 to the third joules is equal to mgh. So what I'm going to take is the mass of an average person, and I'm not an average person. I'm, average height, but I'm not average weight, more like 100 kilograms. So what I'm going to do is instead assume it's roughly 60 kilograms. So the average person might weigh 60.0 kilograms. And of course, gravitational acceleration is 9.80 meters per second every second. And then h is what we're solving for here. So I can go ahead and solve for h by taking 119.4 times 1,000. And I'm going to divide that by parentheses 60 times 9.8, close parentheses. And that gives me, in fact, 200. Yeah, this was right. 203.1 meters. So that's the actual height. That's not what I expected to get, though. What did I do? 500 calories. Oh, stupid me. I wrote my conversion factor upside down. I just finished teaching y'all that, and I literally wrote it down, and I remembered correcting myself for it. So let's do this real quick. Sorry about that, everybody. Jesus. I guess I should be happy that this isn't as bad as what happened yesterday. Yesterday, I actually started my 241 class by teaching 20 minutes of 242. That was not what you're supposed to do. So, looking back at what we're supposed to have here is 1 kcal, and that is a thing that I've always had an issue with. Is sometimes I forget whether the 4.186 goes with the joules or goes with the calories. But the mechanical equivalent of heat found that the 1 kcal is 4.186 kilojoules. So 4.186 kilojoules was what I was supposed to do. I apologize for that. Everybody, make sure you make your corrections in the in your notes. So it might just be a big X that you put over it, but the main thing is we're now taking the 500 and we're going to multiply that by 4.186, and that gives me 2,093 kilojoules, which I can also write as 20. Let's say 2.093 with that one extra sig fig. And I moved the decimal 3 places to the left, so I really need it to be 3 places to the right. So I'm going to multiply this times 10 to the 6 joules. So that's it in pure joules is 2.093 times 10 to the 6 joules. And with that in mind, now I set that equal to MGH, and again, that's going to be 60.0 kilograms times 9.80 meters per second times H. And then if I solve for H, that's going to be divided by, so I'm taking the 2.093 times 10 to the 6, and I'm dividing it by parenthesis 60 times 9.8, close parenthesis, and that gives me 3,560 meters. So about 3,600 meters if we really wanted to choose two sig figs. I'm assuming three sig figs here, but that's it if the body was truly 100% efficient. But it turns out the body is only about 20% efficient. So the human body really only gets to spend about 20% of the energy it takes to cover this distance. So in principle, what you need is in reality not the 3,560 meters, which is the answer that the book was more or less asking for, but to make it more real, what we have to realize is that 0.20 times the energy that the person expired will be set equal to mgh. So I'm going to take 0.20 times the energy that the person ate, which is the 2.093 times 10 to the 6 joules, and I'm going to set that equal to 60.0 kilograms times 9.80 meters per second times h. And I'll put a h on this with a subscript r for the real height. So the real height would be specifically uh, zero point 0.2 times 2.093 times 10 to the 6. That gives me obviously a smaller amount of energy. It gives me 4.186 times 10 to the fifth. So now I'm going to take that 4.186 times 10 to the fifth and I'm going to divide that by 60 times 9.8. And when I do that, I get more like 711.9 meters. So that's a more realistic figure. And again, if we assume three sig figs, then, or excuse me, yeah, three sig figs, then we really only have about 712 meters is how high you'd have to climb to wear off that much energy or to run off that much energy. Anybody have any questions on that? Sorry about that boo boo on the conversion factor. Feel free to let me know if you think I'm making such a mistake. I understand I'm teaching it to you, so I suspect most of you won't necessarily know. But if you do know, let me know. It's okay. I really truly appreciate it. It's not like it's going to anger me. So, no questions. All right, so that was the first example from within chapter 19. Now, what we have to do is, as I told you, I had to make sure you can distinguish between heat, internal energy, temperature, and all that good stuff. So now, what I want to point out is the internal energy. I already told you this, but I'm going to read exactly the words it says. The sum total of all the energy of all the molecules in an object is called its internal energy. Sometimes thermal energy is used to mean the same thing. We introduced the concept of internal energy now since it will help clarify ideas about heat. So, what we're going to do is now that we have that idea, we're going to imagine a ideal gas that's actually monatomic. So what we're picturing here is an ideal gas made of like helium or neon or argon, specifically because helium, neon, and argon, of course, they're noble gases. They pretty much just make a atom. In other words, unlike hydrogen, nitrogen, and oxygen, hydrogen doesn't like being by itself, nitrogen doesn't like being by itself, and oxygen doesn't like being by itself. So they generally form diatomic molecules, H2, N2, and O2. That's not what we're shooting for. We're shooting for single billiard ball like atoms. So that's what a monatomic gas is. And the reason why is even if you go up to diatomic, that's two atoms. And because of it being two atoms, you get a bunch of different types of energy. In addition to the energy that we learned about earlier when we were talking about the temperature in chapter 18, we learned that the atom could move left and right, or the molecule could move left and right, and that was maybe the kinetic energy as a result of V sub x, and they could move in and out, and that was the kinetic energy maybe due to V sub y, and they could move up and down, and that was due to kinetic energy due to V sub z. Those are translational kinetic energies, and those are the only kinetic energies that matter when it comes to being directly proportional to the temperature. But the atom could, in principle, rotate this way about an axis like this. right? It could also rotate this way about an axis like this, and it could also rotate this way about an axis like this. But it turns out since Atom's diameter and radius is so small, those energies are really insignificant and they don't come into play at all. So dealing with a monatomic gas, you only have really the translational kinetic energies. If you move up to a diatomic gas, you still have the kinetic energy as a result of x velocity, kinetic energy as a result of y velocity, kinetic energy as a result of z velocity, but you also have kinetic energy associated with 1/2 I omega squared from the two atoms rotating about an axis through the top. You also have it from the two atoms rotating through an axis through the front, and that would be another one. Now, in principle, you'd also have it through an axis like this, but that's again two molecules rotating about their center, or two atoms rotating about the bond that connects them. So it's literally about the center of their individual atoms, and that's insignificant, but that is a relevant thing. So we've got two more types of kinetic energy: 1/2 I omega squared and 1/2 I2 omega squared as well. So that's just from those two. But in addition to that, we also have the potential energy associated with them acting like they're connected by a spring. So that's another potential energy. And then, of course, that potential energy is sloshing back and forth between being kinetic energy and potential energy. Okay, so you can see there's a bunch of different types of energy that comes from diatomic gas, and if you go higher, it's even more. Like, if you go to water or CH4 or something like that, you'll find that every one of those bonds between one atom and another can sort of act like a rotation axis, and you'll get another 1/2 I omega squared as a result of those. So it can be a lot. So with all that in mind, what we're doing is first starting off with an ideal monatomic gas. So for an ideal monatomic gas, the internal energy, and the symbol we use for this is just E. In our book anyways, we use E with a subscript INT. That's internal energy. And what we know is, because we've reduced it to monatomic, the only thing we can have is the kinetic energies associated with translation. And we already figured out that that was the 1/2 m v squared bar. So if we assume that there's n molecules slash atoms, but in this case it literally has to be atoms, then the potential or the internal energy is n times 1/2 m v squared bar. And we know that's the average kinetic energy, so that's n times k bar. But we also know that K bar is equal to, recalling K bar is equal to 3/2 KT. Then we also have 3/2 N times K times T is the internal energy for an ideal monatomic gas. Now, if you also recall that we could replace the n, so I'm going to write this result right here before I move on. So this result is E internal is equal to 3/2 n kT, and that's for an ideal monatomic gas. But if you also remember that K is equal to the ideal gas constant R over Avogadro's number, then you can see that N times K would be N over NA, over Avogadro's number times R. And of course, N divided by N sub A is lowercase n, the number of moles, because big N is the total number of atoms, and if you divide that by Avogadro's number is the number of atoms per mole, so you're literally converting the number of atoms to the number of moles. So now we can see that there's yet another formula, and that other formula is E internal is equal to 3/2 N times R times T. So that's the internal energy of a ideal gas that is monatomic. Anybody have any questions on that? Okay, so this is some of the stuff where you want to go ahead and try to, read the chapter as well as you can, and sometimes it takes a quick reading is better than a slow reading. Sometimes I've always just read really, really slow, but I've learned from a lot of different authors. They suggest read really fast, but read it multiple times. So maybe that works for you. Give that a try. But so far, what we've come up with is this form of energy, and we also discovered an equation for raising the temperature of a substance and finding out how much heat that is. So that's another equation. Let me go ahead and box that off so everybody will know as well. So this is the other equation that we've introduced so far. Q is equal to mc delta T. Remember, C is the specific heat. And your book actually gives a table of specific heat values in table 19.1. So you can actually look those up. And what you'll see is they come in joules per kilogram Celsius degree, but they also come in calories per gram Celsius degree as well. And you'll see that, for instance, water has a really high one and metals has a very low one. You also see some of the typical insulators have low ones as well, or excuse me, has high ones as well. But you'll find that water is one of the best insulators there are because it has one of the best specific heats. So just pointing that out, we can go on to section 19.3, which is on specific heat. So I'm going to go ahead and point this equation out again. The equation that we have is Q is equal to mc delta T, where delta T is supposed to be T final minus T initial. Remember, any capital delta like that, when they're the triangle with the point pointing up, that's supposed to mean final minus initial of whatever variable comes to the right of that delta, unless we explicitly state otherwise. And you're going to see we're getting ready to run into a case where I'm going to explicitly state otherwise for a very good reason. But that's what delta T is. C is the specific heat. Q is a positive quantity. It's Q is just heat, and heat is the transfer of energy from one object to another or whatever. It's positive if heat is going into the system you're studying, and it's negative if heat is lost from the system. Okay. Uh, Additionally, if you have an issue where there's multiple values of specific heat for temperature, various temperature ranges, or if you're lucky enough to literally have a formula for the specific heat as a function of temperature, then you can also use Q is equal to the integral of m times C of T dt, like that. So those are your two equations that you could use. Occasionally, I will see a problem like where you're supposed to use Q equals the integral of mc of t dt as a homework problem, but that's just about it. Maybe in reality, they might have companies that work on specific heats of certain substances as a function of temperature, and then they could use that in real life. It's just in the classroom we normally don't run into that, except for, like I said, problems just to teach you about it. So that's what the specific heats are. So let me give you just a couple of ideas of what the specific heats are. For instance, the specific heat of aluminum, which is one of the things we'll use in our lab, is 900 joules per kilogram Celsius degree. I'm used to using it in calories, so it's also 0.22 calories per gram Celsius degree, but that's also 0.22 kilocalories. Oop, I should write that as a lowercase c before somebody gets confused. Kcal per kilogram Celsius degree. Noticing going from the middle symbol to the rightmost symbol, I multiplied top and bottom by 1,000. That's why it's still the same quantity. Some other examples, for instance, are glass. The specific heat of glass is 390 in those units, and it's of course 0.58 in these units, and those units, of course, as well. So that gives you some idea of what things are. Now, steel is another one we'll use. Steel or iron, you can pretty much use them interchangeably. Remember, iron is Fe, but steel is iron, in which you add some other substances, always some carbon, but sometimes some. Uh, Actually, I forget some of the things that they put in it, but anyway, it's not that important right now. But there's other compounds you put in it, like chromium and stuff of that sort. And that changes the properties. Sometimes it makes it, more brittle. Sometimes it makes it more soft. Sometimes it makes it more hard. All sorts of stuff changes temperatures at which it melts, changes temperatures at which it solidifies, all that good stuff. But for iron, the specific heat is 450 in the joule unit. So 450, but it's also on the order of 0.11 in calories per gram Celsius degree, or in kilocalories per gram per kilogram Celsius degree. Water, which is a big one here, so CH2O, and I'm specifically going to say at 15 degrees Celsius, has a specific heat of 4,186 joules per kilogram Celsius degree. That's also, of course, 1.00 calories per gram Celsius degree and 1.00 kilocalories per kilogram Celsius degree. However, if you look at C, specific heat of water, specifically ice, which is at -5 degrees Celsius, if you're looking at that, then you're looking more like 2100. And of course, that's closer to 0.50 in these units. And if you're looking for steam, it's quite a bit different as well. CH2O, steam. And in this case, it's at 110. In that case, we find that it's closer to 2010 joules per kilogram Celsius degree and closer to 0.48 calories per gram Celsius degree. So that gives you some idea of roughly what the specific heat of various things are. Your book also gives you protein and the human body. For instance, the specific heat of the human body is roughly 0.83 calories per gram degree Celsius. So you can see it's, acting mostly like water. It's acting like 80%, 83% as big as water. Protein, on the other hand, has a specific heat of zero point 0.4 calories per gram Celsius degree. So now let's show you how to use this stuff by trying example 19.2. So let's say example 19.2. Again, I'm reading it. This one's called How Heat Transferred Depends on Specific Heat. It says how much heat input is needed to raise the temperature of an empty 20 kilogram vat made of iron from 10 degrees Celsius to 90 degrees Celsius. And then part B, what if the vat is filled with 20 kilograms of water? So what we want to know is Q equals question mark. This is part A, by the way. Actually, I should probably leave myself a little bit more room than that. So I'm going to say part A, Q equals question mark for 20. I'm going to go ahead and make this 3 sig figs, even though they only gave us 20 kilograms of steel slash iron. They actually asked for iron, but I'm reminding you guys that steel and iron are somewhat interchangeable. Uh, from 10 degrees Celsius, and I'm going to call that 10.0 degrees Celsius, to 90.0 degrees Celsius. And then part B is Q equals question mark for 20.0 kilograms of steel plus 20.0 kilograms of water. Okay, so that's what we're trying to solve here. Our solution is going to start off with Q equals MC delta T, and the C for steel We just wrote that down, was 0.11. Actually, since they gave us in kilograms, no, we'll do that. Uh, I'll end up doing both anyways, so I'll say 0.11. And this would be kcal per kilogram Celsius degree. And specific heat of water, of course, is going to be equal to 1.00. And that also would be kcal per kilogram Celsius degree. So that's really what we need. We'll start off with part A. So Q is equal to 20.0 kilograms times 0.11 kilocalories per kilogram Celsius degree times 90.0 degrees Celsius minus 10.0 degrees Celsius. Remember, when we subtract 90 degrees Celsius minus 10 degrees Celsius, we sort of use a little note taking idea to remind us that it's been subtracted. So we'll call that 80 Celsius degrees instead of degrees Celsius. Just something that is good for keeping track of everything you're doing. So I'm going to say 20 times 0.11 times 80, and that should give me 3 sig. No, it only gives me 2 sig figs because the specific heat's only to 2 sig figs. So that's 1,700, or excuse me, 176 kilocalories. And we could, of course, convert that to joules because we know that 1 calorie is equal to 4.186 joules and 1 kilocalories equal to 4.186 kilojoules. So 176 times 4.186 is equal to, and I'm double checking, make sure I put that in the right order just to make sure. Yes, 1 kilocalorie is 4.186 joules. So I'm multiplying that by 4.186, and that gives me 737 kilojoules. So that's my answer for Q for the empty vat. Now, when I want to do part B, which is the empty vat plus 20 kilograms of water, what I know is I just need to take that calculation I did for the steel and combine with that the answer that I get for water. So I'm going to say QH2O, and that just means how much heat additionally is going to be required for the 20 kilograms of water. So that's 20.0 kilograms times 1.00 kcal per kilogram Celsius degree times 90.0 degrees Celsius minus 10.0 degrees Celsius. And in this case, it becomes 20 times 80 basically. And that's 1600, which is way bigger than what we had before. And of course, I can multiply that by 4.186, and that gives me 6,700, and that's kilojoules. So that's just the water part. That means Q total would be equal to 1600 kcal plus 176 kcal, which you can see is really a small addition to it. So 1600 plus 176. The last digits don't even line up. Technically, the 176 has only the 1 and the 7 are significant, and only the 7 and the 3 on the kilojoules are significant. When I add these two together, I get the wonderful number 1776. But in this case, we only have 2 sig figs to be added, so these last two digits are not, and that's in kilocalories, which can also be in joules by multiplying it by 4.186, or actually in kilojoules, and that of course gives me 7,434 kilojoules is equal to Q total. So that's the answers for this. Like I said, we got around 176 kilocalories for part A versus 740, of course, for the kilojoules, and then for part B, we got 1,776 kilocalories, which we could also interpret as roughly 7,400 kilojoules. Any questions on that? Now, your book asks a very good conceptual question here, so I'm going to go over it. I'm not going to actually write it, but the conceptual question is this: a very hot frying pan. So it says you accidentally make a bad mistake by letting an empty frying pan get very hot on the stove, 200 degrees Celsius or more. What happens when you dunk it into a few inches of cool water in the bottom of the sink? Will the final temperature be midway between the initial temperatures of the water in the pan? Will the water start boiling? Assume the mass of the water is roughly the same as the mass of the frying pan. So what we know, and I want you guys to have already thought about this, so you should, take a poke at what you think the answer is before I answer it. But what you need to think about is, in this case, we're sort of pretending like all the heat that's going to be lost from the frying pan is going to be gained by the water. Well, that means MC delta T is equal to MC delta T, but in one side the C is 1 and the other side the C is 0.11, right? So in order for the 0.11 side to come out to the same as the 1.00 side, the temperature change is going to have to be a lot larger on the 0.11 side. So what that means is the steel plate or the steel skillet, if you will, or whatever, that is actually going to change the temperature a lot. In other words, its change in temperature is going to be on the order of 10 times or at least 9 times larger than the change in temperature of the water. So, for instance, if the water was 20 degrees Celsius and the pan was 200 degrees Celsius, the difference between those is 180, and a tenth of 180 is 18. So we'd expect the water to go from 20 to maybe 38, whereas the pan would go down from 200 to 38. Does that make sense? Now, it also wouldn't boil because it turns out, in addition to needing 1 calorie per gram Celsius degree to change the temperature by 1 Celsius degree, you also need something called the latent heat to convert the water from a liquid state to a gaseous state. And that can sort of be thought of as the energy required to break up the pseudo bonds between adjacent molecules in the liquid water. So it's not going to cause it to boil. Now, if you did the opposite, if you, for instance, made a pan that was, thousands of times heavier than the water and was 200 degrees Celsius, and then you just threw a drop of water in there, which you probably might have done before. That's actually one of the things you do to test whether your frying pan is hot enough to cook steak, for instance, is you throw olive oil across of it. But you can do it with water as well. If you did it with water, what you'd see is the bottom surface of the little bead of water would actually quickly boil because of the intense heat, especially if it's over 212 degrees Celsius. It's going to boil, and that's going to cause a little wafer of air between the drop of water and the pan, and that's called the Leidenfrost effect. That's what we use when we do physics demos with liquid nitrogen, so that we can actually literally stick our hands in liquid nitrogen. That if we really left it there, our hand would literally freeze solid and break off because it's like negative 147 degrees Celsius. But because of the Leidenfrost effect, I can go, and I don't recommend anybody do this, but I've done it before. I take my hand and I scoop up the liquid nitrogen, and it doesn't burn me at all because it builds this little wafer of air between it and the surfaces of my hand and makes it nearly frictionless, which is all interesting by itself, and it keeps it from burning me. I also do tricks like, I used to put it in my mouth and spit it out. That's super, super, super dangerous. That could actually, kill you, period. If it goes down your esophagus, it could literally kill you. That's not a good thing. But you got to, practice a little bit and be careful and cautious. But the other thing it can do is it can fall in a cavity, and then that Leidenfrost effect won't be able to work, and you could literally have a tooth explode, and that's painful too. So, anyways, that's some more physics and concepts and ideas that you need to understand. So, hopefully, this helped you with that. Anybody have any questions on that one? So a big portion of this chapter is about calorimetry, and as you can see, it's called calorimetry, and you can probably see why I often choose to use the calorie version instead of the joule version. Specifically because the numbers I know off the top of my head pretty well. I know roughly steel is 0.11. I know aluminum is 0.22. I know tungsten, or excuse me, not tungsten. I know zinc is 0.09, and I know water's 1. So those things are just stuff I know off the top of my head because I've used them a lot. And that brings us to example 19.4. Remember 19.3 was a conceptual example. So now I'm going to do example 19.4. Yeah, 19.4. So this example is called "The Cup Cools the Tea." If 200 cubic centimeters of tea at 95 degrees Celsius is poured into a 150 gram glass cup initially at 25 degrees Celsius, what will be the common final temperature T of the tea and cup when equilibrium is reached, assuming no heat flows to the surroundings? So what we're pretending is this heat transfer is going to take place pretty quickly and no heat will be lost to the environment. That's not the best of approximations, but you could make it very accurate if you used a calorimetry cup. We're not using that here. We're just using a cup, but it'll still give us a good ballpark figure. So what we have is 200 cubic centimeters of tea. And tea, if you think about how you make tea, it's this itty bitty bag that you put in very, supposedly, if you're in Great Britain, extremely hot water. And you just basically are soaking the individual petals or leaves, if you will, of tea into the liquid, and then you just pull the tea bag out and toss the tea bag, or maybe reuse it or something like that. But you can see you've added very little substance to the water. Now, if you're making American tea, which includes Southern sweet tea, then you're going to add a butt ton of sugar to it, and sort of all bets are off at that point. So if you actually are talking about really sweet tea, you should probably do some experiments to determine what the specific heat of sweet tea is at the sweetness level that you're used to doing. But in this case, we're going to just pretend it's tea, which is essentially water. And since it's essentially water, we're going to say this is equivalent to, since the density of water is 1 gram per cubic centimeter, this is equivalent to 200.0 grams of H2O, and that H2O is at 95 degrees Celsius. And I'm going to call that 95.0 degrees Celsius. Okay. We also have 150 grams of glass at 25.0 degrees Celsius. And what we want to know is T equilibrium. And I'm just going to say that right there. Now, the solution is going to involve Q is equal to MC delta T. I'm going to need the specific heat of water, which is 1.00 grams per, calories per gram Celsius degree. And I also need the specific heat of glass, which I wrote down a second ago, but that's not one I commit to memory, so I have to go look it up. For glass, we found out the specific heat was 0.58. So this is 0.58 calories per gram Celsius degree. Now, there's two ways that this is often solved. One way is uh, delta Q is equal to 0. In other words, we take Q, that's one way of writing it, but we could also do it as, let me do it this other way. The summation of the Q. I don't like using the delta. There's a whole other problem with that, but the summation of the Q's is equal to 0. So what you're doing in this case, if you use this version, some of your Q's are going to come out negative because T final minus T initial is a negative quantity, and other Q's are going to come out positive because T final minus T initial is a positive quantity. The problem with that is once we start changing state, then we'll have to remember exactly what signs go with the change of state, latent heat. So there's a latent heat associated with changing from a liquid to a solid, or from changing from from a gas to a liquid, and one way you go, it's positive, the other way you go, it's negative. So I've just consistently found that students, and including myself, often made careless mistakes in a test, in a high stress test situation, while trying to come up with the proper sign for the latent heat. So I don't use the sum of the Q's equals zero. The other way we use, and this is what I do use, and your book shows both, by the way, is one collection of things will lose heat, and that heat will be called Q lost. And the other things in the reaction, in the thermal reaction, will gain heat, and all those things, I'll add all their gains of heat together and put it on the other side. So if you put Q loss equals Q gain, then what happens, and this is what I warned you about earlier, this is the case where you have to forcefully make the delta T go against the definition of delta. We have to have all these terms be positive when we use Q loss equals Q gain. So you always got to do big numbers minus small number for the delta T's instead of final minus initial. And when you go to use a latent heat later, you're just going to choose that as positive as well. So it makes it a lot easier for me. So in this case, what we have losing the heat is the T. So I'm going to put MC delta T for the T is 200 grams times 1.00 calories per gram Celsius degree. And then, of course, that is going to go from a high temperature to a low temperature. So I'm going to put the high temperature first, which is 95.0 degrees Celsius minus T. Now, the other side, the glass, will be gaining heat, and that has a mass of 150 grams. So 150.0 grams. The specific heat is 0.58 calories per gram Celsius degree. And then again, in this case, the temperature is actually going up. So I'm going to do T minus 25.0 degrees Celsius. And our job is to solve for T. So the first thing I'm going to do is take 200 times 1 and multiply that by 95. And that should give me 3 sig figs, and it gives me 1.900 times 10 to the fourth. And notice in multiplying grams times calories per gram Celsius degree times Celsius degree, I just get calories. So that's the first part. Now I'm also going to take that 200 grams, multiply that by 1.00 calories per gram Celsius degree, and then multiply that by T. So in this case, I'm going to get 200.0 times T. Now, technically, the unit left will be calories per Celsius degree times T, but I'm going to leave that off because it's kind of a pain to write. So the units of that 200 is calories per Celsius degree. Now I'm going to do the same thing over on the left hand or right hand side. I'm doing 150 times 0.58. That is actually, I'm only supposed to have two sig figs on this side, so that's times 0.58. That gives me 87.0, and in this case the units of the number 87 would be calories per Celsius degree times T, just like the 200. So I'm going to put the T there. But now I have to take the 150 times the 0.58 times the 25. And that also gives me only 2 sig figs. And it's going to be separated by a minus. So I'm going to say 2.18 times 10 to the third. And the units left there are just calories. So you can see that I can combine the calories together by pulling the negative 2.18 to the other side. So I'm going to say add that to 1.9 times 10 to the fourth. And that gives me 2.12 times 10 to the fourth calories, and I'm going to pull the t terms to the other side. So that'd be 87 plus 200. That's going to be 287.0 times t. So now all I have to do is divide both sides by 287. And remember, that is calories per Celsius degree over 287 calories per, and that's per Celsius degree. And in this case, I'm going to say divided by 287, and that gives us only 2 sig figs, so it's 73.8 Celsius degrees is equal to T. And I don't know why I've got, oh, they used calories, so that could be a slight difference. All right, 25 degrees Celsius, that was good. Make sure I copied everything correctly. I used 25 degrees Celsius, I used 150 grams, I used 95 degrees Celsius, and I used 200 grams. Uh, they got a slightly different one, but I'm assuming this is partly because they use slightly different units. They use the Celsius, or excuse me, the joules, and there's some conversion difference between them. So I don't understand why I got 86 instead of 73, and I thought I got 86 the last time I calculated. So there might be a careless mistake that I made somewhere in this arithmetic. Did anybody find any mistakes I made? Let me double check my numbers. 200 times 95. That gave me 1.9 times 10 to the fourth. That looks good. 200 times 1 times negative t gave me negative 200. That's good. 150 times 0.58. That gives me 87.0. So that's consistent with what I had on the right side. 150 times 0.58 times 25. That's 2175, which is 2.18 times 10 to the third. That looks right. And then when I pull the 200 to the right hand side, that's 287. Yeah, I get 73.8 again. I don't see any problems with anything I did. All the math looks right. All the equations look right. Uh, there was just liquid, nothing else in there. MTCT 95 minus T and M cup T C cup times, and which did they use glass for the cup? Yeah, they did use glass. And what they used for their specific heat of the cup was 840. If I look back and see what that is in joules per kilogram, see if they're using the same thing as I did. Glass. Ah, there's the problem. I said my specific heat of glass was 0.58. Their specific heat was 0.20 calories per gram Celsius degree. So, yes, everything was done right. I don't know what I got the 0.58 from. I must have, when I looked back at my notes to check it out, I must have looked at the wrong thing. Nope, I just wrote it wrong last time. So, yeah, all of that's done correctly, but I'm going to put a big line through this so everybody realizes that this is an error. What did I look at when I saw 390.58? Oh, I was looking at copper, one line above it. But I also mixed that up because I went to alcohol for this for the specific heat of in calories. So yeah, that's just all jacked up. So yeah, all the physics was done right. All the numbers I used were consistent with what I had said, but they're not really the correct numbers. So if C equals 0.20 calories per gram Celsius degree is used for C glass, you obtain T equals 86 degrees Celsius. That's what's supposed to happen next. Yes. So don't worry about this one. This one was actually done okay. It's just a matter of me copying the wrong value down from the table. Uh, so that is something, by the way. Remember, the chapters have tables of quantities. They're sort of expecting you to use those tables. If you go on the internet, you'll usually find close enough values that it's not going to be any problem. But sometimes you'll find values that are a little off, either because the internet's wrong or the book's wrong. But the main thing is when the people like me, I used to be the one of the people that was hired to solve these problems and make sure they're all correct. When you do that, we always use the values from the textbook. Even if we think that might be some error, what we'll do is report that to the author, and then the author will either check it and change it or check it and say that no, we're wrong. But the main thing is all the homework systems are worked with the examples, specific heats and densities and stuff like that coming straight from the book. So, any questions on that one? All right. Well, we have another meeting on Thursday, and I suspect I'll be able to finish up this chapter on Thursday. Uh, it's not too terribly bad, but go ahead and check it out. Let me know if you have any questions. You guys are free to go. Make sure you chat me your first and last name if you haven't done so already. And thanks for coming, and I will see you guys again on Thursday. Oh, don't forget to check out the derivation of V bar on my YouTube channel. Thank you, everyone. Thank you, Miles. Thanks you, Alex. Did you have any question, Miles? He might just be taking a little while to sign out. So I take it that's it. I've got this. These will go up on my Google Docs and the video will go up on my YouTube channel. Have a good day. Bye bye.